This is problem 5 from chapter 13. If blocks A and B of mass 10 kilograms and 6 kilograms respectively are placed on the inclined plane and released, determine the force developed in the link. The coefficients of kinetic friction between the blocks and the inclined plane are 0.1 and 0.3. Neglect the mass of the link. So we will start off by figuring out what the forces are. So I have a normal force acting on block A and on block B, and I have a force of gravity acting downward. So normal force on block A, normal force on block B, force of gravity acting downwards on block A, force of gravity acting downwards on block B. I also have a force of friction acting on each block. So I have the force of kinetic friction for block A and the force of kinetic friction for block B, and I am going to redraw my free body diagram in just a moment. And then I have the link between the two blocks. So the link exerts a force on block A. It also exerts a force on block B. If you look at the system as a whole, so block A and block B and the link, then the force that the link exerts on A and the force that the link exerts on B are both internal forces. So those forces shouldn't appear when you look at the system as a whole. So if I have the force of the link acting in one direction on block A, it should act in the opposite direction on block B. I can guess what direction the link is, I can guess the direction that the force of the link is going in. And if I guess wrong, then I'll just get a negative sign when I solve. So I think that it is going upward on block A and down on block B. But if it's wrong, it doesn't really matter. You just get a negative sign and then you know it's pointing in the opposite direction. So now I'm going to redo my free body diagram for block A. So I have the normal force pointing perpendicular to the surface, the force of kinetic friction for A pointing up the incline, and the force of the link pointing up the incline. And then I have to take the force of gravity and break it down into components. And if this angle is 30 degrees when I break the force of gravity down into components, then this angle is 30 degrees, so this would be the cosine component. And this would be the sine component. Let's do the free body diagram for block B. And we have the force of the link pointing down the incline in the opposite direction of whatever I said it was for block A. And the normal force and the force of kinetic friction for block B. And the force of gravity, which I need to break down into components. So I have the cosine component FGB, cosine of 30 degrees, and the sine component. Then first, let's do the sum of the forces in the y direction, which is usually a good idea when you are looking for kinetic friction. So we have, this is the y direction, and let's say that this is the x direction. So in the y direction, the acceleration is equal to 0. So the normal force is equal to FGB cosine of 30 degrees. The force of gravity is just equal to the mass of block B times little g. So the normal force is equal to, the mass of B is 6. So that's 6 times 9.8 times cosine of 30 degrees, which is 51 newtons. And the force of kinetic friction then is equal to 0.3 times 51, and that is 15.3 newtons, and we will just save that for later. Then we'll look at block A. The sum of the forces in the y direction is equal to 0. That means the normal force is equal to FGA cosine of 30 degrees. Just like we did for block B, we put in the mass, which is 10, and then 9.8, I should have said 9.81 there. 9.81 times cosine of 30 degrees, and that gives me 85 newtons. And then the force of kinetic friction for block A is 0.1 times 85, which gives me 8.5 newtons. Okay, so then the next thing to do is look at the sum of the forces in the x direction. So the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. We have, going in the positive direction, FGB sine of 30 degrees, so that's 10 times 9.81 times sine of 30 degrees, and then we have minus FL minus the force of kinetic friction, which is 8.5, which is equal to the mass of 10 times the acceleration in the x direction. Now we do the same thing for block B. And we have, going in the positive x direction, this would be the mass of 6 times 9.81 times sine of 30 degrees plus the force of the link minus the force of kinetic friction, which is 15.3. That's equal to the mass of the block times the acceleration in the x direction. Now I'm going to take these two equations and add them together. Let's call this equation 1, and we'll call this equation 2, and we're going to say equation 1 plus equation 2. So at everything that's on the left-hand side of both equations, you can even combine the 10 and the 6 here and say that's 16 times 9.81 times sine of 30 degrees. Then if you add negative FL and plus FL, you get 0. And then I have negative 8.50, which is the force of kinetic friction on block A, and minus 15.3, and that's the force of kinetic friction on block B. And then adding the right-hand sides, that's 10 times the acceleration plus 6 times the acceleration, which is 16 times the acceleration. And now I would like you to notice that if we did our free body diagram for the full system, we'd have the force of gravity, and this would be the x component of the force of gravity for the entire system. We'd have friction on block A and friction on block B. And then we'd also have the normal force in the y direction and the y component of the force of gravity. And that would be equal to the sum of the forces in the x direction for the entire system would be equal to the mass of the entire system times the acceleration in the x direction. Well, you can solve this for the acceleration on your own, and you should get 3.42. And then after you get that, what do we want? We want the force of the link. You could either use equation 1 or equation 2, so then use equation 1 or equation 2, and in either case you should get the force of the link is equal to 6.4 newtons. And that concludes problem 5.